Hello, and once again, welcome to another fascinating topic, lithium ion battery. The principle, the chemistry behind lithium ion battery. I am SS Tripathi, and my channel's name is SST Chemistry. Now, you must have known that the battery you use in your mobile phones, in your laptops, in electric scooters, electric cars, commonly called electric vehicles, EVs, or even the battery used for storing electricity from solar panel, all are nowadays lithium ion batteries. Therefore, sometimes these are called solar batteries because they store the solar energy that is produced from solar panels. The electricity is stored in the solar battery. Instead of sending to the national grid, you can also store in high capacity lithium ion battery, and that is in that particular case called solar battery. All these miracles of lithium ion battery is the hero lithium. Lithium is the hero in the lithium ion battery, and we'll see what crucial role lithium or the lithium ion plays in this magical battery. Now, in the market, only two lithium ion batteries are capturing the entire battery market, lithium ion battery market. This is NMC or NCM, nickel, cobalt, manganese lithium battery, and the other one is LFP, lithium iron. F stands for iron phosphate lithium ion battery. We shall be knowing in details how it performs. Just wait a bit. Now here you must have known that just like your petrol pumps, you will find many charging centers for the electric vehicles. You can just plug in and charge it and again unplug and carry on your tour. Now, let me tell you why lithium ion batteries are so very popular. It is because of its lightweight. Lithium is the lightest metal, high performing, because its energy density, that the energy it can store per kg of the battery, is high, much higher than other conventional batteries. Those were in use, they have high specific power, higher voltage, low maintenance cost, and highly durable. Long time it will go, and it has got a high DOD, depth of discharge, means it can discharge up to 95% and there will be no detrimental effect or bad effect on the battery. You can use it to the extent of 95%. And I'll just tell you, the energy density of lithium ion battery is 300 watt hour per kg, while the other batteries which were popular earlier is the nickel cadmium battery, nickel metal hydride battery, lead acid battery. They were having only 75 to 100 watt hour per kg. They were heavy, these are light, and the voltage is also high here in lithium ion battery. It is nearly 4 volt, while in all other cases it is 1.5 volt per cell. Several cells, while combined in a series manner, they produce a battery. Battery is nothing but a series combination of multiple single cells. And most importantly, the lithium ion battery do not have memory effect. That is why they are durable. Memory effect means the earlier batteries, if you discharge to the extent of 25%, 30% and again charge, that means you partially discharge and again charge, then it will remember the charging capacity is 25%. So with time, the charging capacity will decrease and the durability, the longevity will be less. So there is no memory effect. Whether you discharge 25% and then recharge or 70% recharge, it will never remember what happened during the last discharge and recharge. So the function will not be deteriorated. Now, let me tell you that in any rechargeable battery, you have only two modes. One is called the discharge mode when you use the battery. When you use the battery in your laptop, in your mobile, in electric scooters or electric cars, then you are using them. That is, the battery is in the discharge mode. It is giving you electric current. And in that mode, these cells are called galvanic cells. And they produce electric current out of a spontaneous chemical reaction. Let's take an example of any cell, which is a galvanic cell in the discharge mode. And we will take the lithium cell because we are now going to discuss about lithium batteries. Now let's take the negative electrode, the anode, as lithium metal and lithium ion, a couple. And as cathode, a couple containing cobalt dioxide, a transition metal oxide, and lithium ion. This couple will constitute the cathode or positive electrode, and lithium metal, lithium ion will constitute the anode. And this is called a separator, which will separate the anode from cathode. Just like a divider, separator, or a barrier. Okay. Now what happens during discharge? Supposing lithium metal here is the hero. Lithium ion will be waiting for its turn. But in discharge mode, lithium metal will undergo oxidation, and this loss of electron will be flown through the external wire, and it will come to the cathode. And in the cathode, cobalt is in the higher state, +4 state cobalt dioxide. Now the hero is cobalt dioxide. And of course it will take the help of lithium ion, which has no chemical change. It will remain as +1, but cobalt will undergo reduction from +4 to +3. It will become LiCoO2, where cobalt is in the +3 state by accepting one electron. So cathode in this case will involve reduction, gain of electron, and anode will involve loss of electron or oxidation. Everywhere anode involves oxidation, because anode starts from the vowel A, oxidation starts from the vowel O, and cathode starts from the consonant C, so also reduction starts from the consonant R. So anode always involves oxidation, cathode reduction. So in the discharge mode, when it is a galvanic cell, the anode has a higher oxidation potential. You will learn in a higher class that anode or negative electrode is in a higher oxidation potential. It has a strong tendency to lose electron. And the cathode has a strong reduction or high reduction potential. It has got a high tendency to accept electron. So these mutual desires will be satiated by us, by middlemen like us, mediators like us. If you combine the anode with cathode by an electric wire, then spontaneously electron will flow from the anode, negative electrode, to cathode, the positive electrode, and we will take the benefit of this current. We can put any load, our laptop, our electric vehicle, or whatever. It will act in the discharge mode. Then let's see what happens during the charge mode. I am showing this in a picture in the same discharge mode, where supposing these are lithium metals, lithium metal will be oxidized to lithium ion. This lithium ion will be flowing through the electrolyte, through the separator or divider or a barrier, to the other side, to the cathode, because it has to take some role during this chemical game. But lithium ion doesn't undergo any change in oxidation number. So lithium ion will migrate, this separator will be so designed, it will allow lithium ion to migrate from here to there or there to here. We'll know that later. And will not allow the physical contact between the anode with cathode. Right? Now electron will go in the external wire from anode to cathode. This is the flow of electron, but the conventional direction of current, as we learn in physics, is the opposite direction to the flow of electron. So we are not going to discuss about the current electricity. We are interested how the current is produced by the flow of electron in the external circuit, right? This is the discharge mode. Now coming to the charging mode, when your battery will be discharged, then you put it under a charger. This is the charger. Charger is nothing but a DC, direct current battery source. Your charger, you have seen a charger. For every recharging system, there is a charger. Because when your battery is discharged, the voltage drops down, then you have to again raise the voltage to the original 4 volt. Or if you have a combination of 3 cells, then 12 volt. 10 cells, you have 40 volt. Depending on our requirement, we will combine individual cells in series and get our required voltage. So what we do in the charging mode, we use a charger which is a DC source, a DC battery. In fact, when we plug it to the town supply, which is AC, alternating current, that AC is converted to DC, and the voltage of that charger, the DC source, must be greater than the voltage, the maximum voltage that your cell, your battery that you are going to use after some time will generate. So this charger should have a higher voltage than that. Then only when it will be used in the opposite direction. Now this is the positive electrode, and this is the negative electrode. Now the electron will flow from the so-called cathode to the so-called anode, because at this time during charging, this cell is no longer a galvanic cell. It is another kind of cell called electrolytic cell, where a non-spontaneous reaction will be happening by the application of electrical energy, this DC source or the charger, in the opposite direction. So in the discharging mode, electron was moving from left to right, anode to cathode of the discharge mode. Now in the charging mechanism, the electron will move from the cathode to anode. I said cathode as per the name on the discharge mode, but actually this electrode will be acting as anode. Therefore I have written this is anode, not cathode. But cathode name we will keep, because we will be using the battery in the cathode mode. But now when you discharge it, if you ask battery, cell, are you a galvanic cell? The cell will say, no, I am so sorry, I am not a galvanic cell. Now I am under charging mode and I am acting as an electrolytic cell. So the cell reaction is opposite. So here lithium cobalt dioxide, where cobalt was in the +3 state, will be again oxidized to +2. Now lithium ion will be released from gel and it will be migrated towards the anode, so-called anode, but now it will act as cathode, where reduction will occur. So the electrons in the outer circuit will come in this direction from the so-called cathode to so-called anode, but actually from anode of the electrolytic cell to the cathode of the electrolytic cell, where reduction will occur. Lithium ion now will pick up electron from the so-called anode and actually cathode, and will be reduced to the metallic lithium and will be deposited on the already existing metal electrodes. So you saw that the opposite reaction happened, so that the original voltage, say 4 volt, or if it is entire battery, say 12 volt, the whole, if it is a 12 volt battery, this charger should have a capacity more than 12 volt. Right? So accordingly the chargers are made. You can't charge your electric scooters by the charger that you use for your mobile phones. Chargers are different for different lithium ion batteries or lithium rechargeable. I mean, any rechargeable battery having a particular voltage will have its own charger depending on its total voltage it can give you. So to sum up, this is a very important thing for school level students, which they often fumble, they miss out, that during discharge mode of any rechargeable battery, it is called a galvanic cell, where it produces electric current out of a spontaneous reaction. Anode, as we kept in the left side, it's not always binding that you saw in the picture, anode in the left side during discharge mode. You can as well show in the right side, doesn't matter. Anode is negative, where electron is coming out, and in the cathode it is going in to the electrolyte. So cathode is positive. And oxidation occurs at anode and reduction occurs at cathode. But when it will be in the charging mode, the anode will be positive. The anode, this is the anode now, is positive, connected to the positive terminal is positive. The signs are opposite. Again oxidation occurs at anode, but anode was negative during discharge mode, galvanic cell mode, and electrolytic cell mode, the anode is positive. Cathode is here, but actually it is the anode of the galvanic cell, but cathode of the electrolytic cell, and cathode is negative. Here is connected to the negative end, negative terminal of the DC battery or DC source, DC charger. So the signs are opposite. Anode is negative, cathode is positive for galvanic cell in the discharge mode, and when it is under charging mode, when you are putting a charger, then your anode in the discharge mode will be cathode and it will be negative, and your anode now your cathode will be now acting as anode, and that is positive. So anode always oxidation, whether here or here, and cathode always reduction, whether here or here. Got it? Now let me tell you a very interesting thing. I have not yet come to the lithium ion battery. A lithium ion battery is the magic. Before that, let me tell you that what is called intercalation. Now, in some crystals, the structures are such that there are layers, parallel layers of the crystal structures. And in between there is space, back-end space. And some other metals or metal ions can be accommodated, can be stored, can be housed in that space in a very regular and symmetric manner. So if that is done, the process is called intercalation. What? Intercalation. That means we say the lithium metal or lithium ion gets intercalated between the parallel layers of the crystal. Particularly when you take graphite, which is one of the allotropes of carbon. I have not yet said about graphite, the use of graphite in lithium ion battery, but I am just introducing what is intercalation. Because I will be using the graphite as the anode. Instead of lithium metal as anode, I will be using they will be using graphite as anode. So the beauty of graphite is they have parallel hexagonal layered structures, and each layer is called a graphene layer, because scientists have also successfully removed individual layers from each other, and each layer is a nano-sized particle or material, and that is called a graphene. So in between the graphene layers, the other atoms like lithium atoms or lithium ions can be intercalated, right? You understand? So the intercalation was first developed by Bessenhard and Eichinger, who prepared a lithium hexacarbon. I mean, this is the carbon layer of the graphite structure, and for every 6 carbon, one lithium atom was being centrally housed. So that is why it is called LIC6, because these are all the hexagonal layers I showed you. These are all hexagonal layers containing 6 carbon atoms, and just below and above each hexagon there will be a lithium or lithium metal or lithium ion. That is why it is LIC6. So they suggested that why not you take this as your anode instead of taking lithium metal. You take lithium ion intercalated with graphene layers. And what happens, I will tell you, that even whatever cathode they were using from the beginning, all the transition metal oxide they were using, they have also similar structure to graphite. They have parallel crystal structures of, I'm showing you nickel, manganese, cobalt oxide structure here. This one, this one, this one. These are parallel structures. I'm not going to discuss in details about the crystal structures, but in between there will be space, vacant space, in which lithium ion will be housed, will be intercalated. So intercalation is possible both in the anode, now it will be a graphite anode, and the already existing metal oxide, the transition metal oxide cathode. So you will see what will happen. I have taken anode in the left side. Doesn't matter, always we will take anode in the right side, left side. It's not that. We can take also in the right side. So wherever there is anode, supposing these are graphite layers, these are the individual graphene layers of graphite structure, which I have not yet introduced. So the lithium ions, not atoms, lithium ions are intercalated inside. Now during the discharge mode, which I have shown here, the discharge mode I have shown here, the electrons will be spontaneously going and giving us electricity, and it will be entering into the metal oxide cathode and bring about reduction here. And during that you will find the lithium ions will migrate, and it will be housed inside the layers of the cobalt oxide or transition metal oxide layers. So it will be de-intercalated from the anode and intercalated in the cathode during the discharge mode. But in the charging mode, opposite thing will happen. Electron will come from the so-called cathode, now acting as anode, and it will be it will be going to the so-called anode, now acting as cathode, and opposite things will happen to lithium ions. Lithium ions will be produced here, and it will be de-intercalated from the cathode, so-called cathode, now acting as anode, and it will be now intercalated in the so-called anode, now acting as cathode. And once the charging is full, you just leave the charger, unplug the charger, and now put it under the discharge mode, where again the same thing will happen. It will act as really anode, and this will act as real cathode, and opposite migration of lithium ion will happen from the anode to cathode inside the electrolyte. Is it not interesting? Now let me tell you in nutshell the historical development of lithium battery. In fact, in the beginning it was not lithium ion battery, lithium metal battery, LMB, lithium metal battery, where lithium metal was used. I have already explained Whittingham. S. Whittingham was the first person in 1974 who developed a lightweight lithium metal battery, a rechargeable battery. I have already told you, but he used titanium disulfide as the cathode material, same parallel structures where lithium ion gets intercalated and titanium was going from +4 to +3 in the similar manner as we found for cobalt in the discharge reaction. It was giving 2-volt battery, 2-volt voltage. So it was of lower capacity at that time. Lithium metal was used as the anode material, sometimes lithium aluminum alloy. Now, you already know that a rechargeable battery like lithium ion battery or lithium metal battery has 4 parts. One is the electrolyte. Inside the electrolyte you can vary, and now it can be lithium hexafluorophosphate dissolved in some solvent like diethyl carbonate and all that. It is liquid state electrolyte in between, inside that will be a liquid electrolyte, and this separator will allow only lithium ions to migrate. Other ions will be too hefty to migrate, and also it will not allow the anode to touch the cathode physically, and so that electrons can migrate inside the electrolyte. There should not be a migration of electron, it should be migration of ions that will conduct electricity inside the battery, and outside the battery, that is the electrical wire, conducting wire, electrons is the hero to conduct charge, conduct current, conduct electricity, not the ions, as you know. And the cathode material, these are the transition metal oxide or sulfide. At that time it was sulfide, now oxides. And lithium metal was the anode material at that time, Whittingham, but now it is graphite. I'll tell you. After some time, J.B. Goodenough, the name is very interesting, Goodenough, and 1979, 5 years later, he also gave another lithium battery but with 4-volt capacity, 3.7 volt capacity, higher voltage, but he used now cobalt dioxide. I was explaining this. This is the discharge mode, lithium metal battery, LMB. We have already discussed the chemistry behind the charging and discharging. But the disadvantage of lithium metal battery, LMBs, is that they are highly risky. Safety risks are very high, because anyway you are dealing with an active metal. Lithium is a alkali metal, may not be highly active than sodium potassium and as sodium potassium, but it is active. So there might be some, it can touch with some water or reactive material inside the electrolyte, and it can burst. It can produce hydrogen and burst. And most importantly, when lithium will be deposited in the charging mode, it will not be deposited in an even manner, in a smooth manner. It will be deposited in an uneven manner to produce projections, some branch-like projections from the anode surface, and those are called dendrites. And if single projections, they are called whiskers. So dendrites and whiskers are formed during the charging process. It will remain as such, it will not go, and after some time these whiskers or dendrites will penetrate through the separator, and it will touch physically the cathode, and there will be flow of electron, and it is called short circuiting, and it will burn, and therefore the longevity was a question mark in lithium metal battery. Then came another scientist, Akira Yoshino of Japan, a Japanese scientist who was first to introduce lithium ion battery. He did not take lithium metal, instead he took graphite. At his time, first he took petroleum coke. The coke obtained from petroleum also carried some amount of, graphite crystals, and in the graphite crystals, there are graphene layers, hexagonal layers. And what happened? And cobalt dioxide he also used, as used by Goodenough. He also used cobalt dioxide as cathode material. And this was not LMB, it was LIB, lithium ion battery, which is the hero now at the present time. And the electrolyte here was lithium, at that time lithium hexafluorophosphate in some liquid solvent like ethyl carbonate, diethyl carbonate. Now what happens here? Let me first explain to you the charging mode. During the charging mode, the same picture I have shown, in fact, that was for lithium ion battery. I faked there to show lithium metal, taking this as lithium metal, but these are actually the different graphene layers of graphite structure. So each graphene layer is a hexagonal two-dimensional network. This contains alternate double bond, single bond, double bond, single bond, and all that. So in hundreds and thousands of graphene layers, they constitute a graphite crystal that is present in graphite and to some extent in petroleum coke. And what happens during charging, when you put it under a charger, the electron comes here and they are stored in the carbon skeleton of each graphene layer. And at the same time, lithium ions, they migrate from the cathode to anode. So-called cathode now acting as anode to cathode, so-called anode. And they will be stored, they will be intercalated in between the graphene layers of the graphite structure. And at the same time, electrons will be loaded onto the carbon skeleton. But magic is that electron will not reduce lithium ion to lithium metal, because this gap is quite high, about 3 angstrom. So electrons cannot jump of its own. It will remain confined in the carbon skeleton and it will be electron rich, and hence increase the oxidation potential of that electrode, this electrode, which is now going to be anode. But now, as long as charging is going on, it is acting as cathode. It is accepting electron, gaining electron, becoming enriched in electron, and lithium ion being housed, intercalated in between the graphene layers. The beauty that lithium ion does not undergo a reduction. It comes and intercalated. And in fact, this migration of lithium ion from this side to this side, that is responsible to capture electron or to attract electron, and more electrons, they are loaded in the graphene layers because of the intercalation of lithium ion. So indirectly lithium ion does heroic role, but without really chemically being a participant. Understand? At the same time, this cobalt was in the +3 state, lower state is oxidized to +4 state. This really acts as an anode, and oxidation occurs here, electron comes in this direction. But the conventional direction of current obviously is the opposite one, because this is the positive electrode, this is the negative electrode, so it is coming in this current direction is this. But let us forget about the current direction. The electron will be moving in the opposite direction compared to relative to the discharge mode. You understood what happens? And the moment we put it under discharge, the electrons which are already stored in the, now it will be called anode, yes, in the graphene layers, will now be released, let loose, because they have a tendency, high oxidation potential. They will be let loose. There will be no chemical reaction, but it will be let loose, and simultaneously the lithium ions will migrate out of the graphene layers, and it will pierce through the separator and go to be intercalated in the layers of the cathode, which is now in the +4 state. It will go to the +3 state because of the participation of lithium ion, not chemical participation but physical participation. They will be intercalated, and accepting electron, they will be reduced from +4 to +3. So lithium ions intercalate the cathode now in the discharge mode, but during the charging mode, it will intercalate the so-called anode, but actually it is acting as cathode. You understood? Now, I have already explained this. Therefore, another scientist who unfortunately was not given perhaps, Nobel Prize, he was a French scientist who, the name was Michael Armand. He named this lithium ion battery as rocking chair battery. That the lithium ion is acting like a settling between anode to cathode material. Now during charging, it is coming from, let me tell only anode cathode. In the discharge mode naming system, it is coming from anode to cathode, and in the charging mode from cathode to anode. So since it is settling between anode to cathode, cathode to anode, just like a rocking chair, so he named this lithium ion battery as rocking chair battery. Right? I am showing you again in a scheme where the blue sign, the blue arrow, they meant for the discharge mode. During discharge mode, electrons in the outer circuit go from the anode to cathode, and these are the layers of cobalt oxide or the mixed oxide, nickel, manganese, cobalt oxide. These are layered structured. So during that time, lithium ions will go here. The blue sign, lithium ions will be de-intercalated from the graphene layers, and it will be intercalated in the cathode layers. But during charging, the red sign, during charging, the electron will go in the opposite direction, and it will be loading the graphene layers. It will not chemically react, it will not chemically reduce the lithium ions. Lithium ions will migrate, de-intercalate from the cathode layers, and it will be now coming and intercalate. It will be housed inside the graphene layers of the anode material. So these are the three scientists for lithium metal battery. The first one is Goodenough and Whittingham and Goodenough. They are the fathers of lithium metal battery. Subsequently, they also moved to the lithium ion battery, but the first lithium ion battery introduced was LIB, was Akira Yoshino, and three of them were given the Nobel Prize in 2019. As late as 2019, they were recognized as the fathers or the creators of lithium batteries, lithium and lithium ion batteries. Now, the two batteries, those are flooding in the market, is an NCM battery and LFP battery. As I have already told you, there is also another NCA battery where instead of manganese you have cobalt, nickel, cobalt. Instead of manganese it is aluminium, nickel, cobalt, aluminium lithium ion battery. LTO, lithium titanate oxide battery. LMO, only manganese battery. So there are so many batteries for different purposes, but the more than 90% of the market is NCM lithium battery or LFP lithium battery, lithium iron phosphate, right? Now let me just in a nutshell, we are going to close within 2 minutes, tell you how the NMC battery is composed. Lithium NMC, lithium, nickel, manganese, cobalt battery, which is more than 60% of the market is NMC, and another 40% is LFP, lithium iron phosphate battery. So let me tell you that this composition, the formula is very long. Lithium, nickel X, manganese Y, cobalt 1 minus X minus Y, O2. If nickel is 1 mole, lithium is 1 mole, the sum total of nickel, manganese and cobalt should be 1 mole. That is why if X is a fraction of nickel, Mn manganese is Y another fraction, and the cobalt fraction is 1 minus X minus Y. So the total will be 1 mole for all the transition metals. Sometimes a non-transition metal like aluminium can be used in LCA battery and lithium. So there will be, what happens, in the earlier lithium, this battery, cobalt is in the +3 state. It is already reduced, right? It is ready for being charged. It is already reduced. Discharging is finished. So this is the original structure of the cathode material. Now this +3, cobalt +3 in the crystal, at several places cobalt 3+ is replaced by nickel 2+, and in other places manganese 4+. For supposing for the replacement of 2 cobalt 3+, +3 the charge is +6, and one of them is Ni2+, the other one is Mn4+, so the total charge is 6+. So there is no charge imbalance. The stoichiometry is restored. But in place of cobalt 3+, at some places you will find Ni nickel 2+ and also Mn4+. Now, there are many nomenclatures. NMC 333, which is same as NMC 111, means equal percentage of the three metals. Nickel 33%, 33.33. I'm so sorry. But it is called 333. And the other metals also equally same 33.33%. So that is why it is called NCM 333 or same as NCM or NMC 111. But if it is NMC 811, it means 80% nickel, 10% manganese and 10% cobalt. Nowadays, the percentage of cobalt is being reduced because cobalt is costly and also pollution prone, causes pollution. That is why there is a restriction of using cobalt. That is why instead of reducing the performance, they are increasing the nickel percentage, manganese percentage to improve the performance of the battery without sacrificing the durability and other stability. So cobalt percentage is being reduced. Now this already I have shown. Nowadays they are not taking cobalt alone, but a mixture of other transition metals like nickel and manganese to have a greater performance stability. Now, during the entire discharging process, manganese, cobalt will be in the +3 state because +4 will be reduced to +3. It will be continuously being converted to +3, and nickel from +4 to +2 because those cathode will be undergoing reduction. But during charging mode, the cobalt 3 plus will be converted to cobalt 4 plus, nickel 2 plus will be converted to nickel 4 plus. Have you heard about nickel 4 plus and cobalt 4 plus? Yes, it happens. But manganese 4 plus that does not undergo any change even in charging and discharging mechanism because but its presence gives extra stability to the battery. Therefore, manganese has been used, but it does not play chemically. And the different companies which they manufacture LIBs are Audi Electron, GE, General Electronics, BMW i3, BYD Yuan, EV 536, Chevrolet, Bolt, Hyundai, Kona Electric, Jaguar, Nissan, they all produce NMC battery. But Tesla is another famous company. It produces NCA, aluminum based, not manganese is not there, aluminum, and LFP. The LFP battery is only manufactured by Tesla company, LFP, lithium iron phosphate batteries. Now, let me tell you the next generation battery. Now, we were previously hating lithium metal battery. Why? Because dendrites, they will burn out because of highly reactive. But if that is stemmed, if that dendrite formation is totally eliminated and the activity is reduced, then LMBs are more resourceful because they can have energy density greater than 400 kilowatt. Greater than 400 kilowatt, now 300 kilowatt per kg. Not kilowatt, I'm sorry, watt hour. There is no no kilowatt. It is watt hour, I'm so sorry. Watt hour per kg. There is no kilo. It is only watt hour per kg. It was 300. Now it will be more than 400 and voltage will be more than 4.5. So for that, scientists are going on very hard to find out a solid phase electrolyte. The electrolyte should be a solid one where migration of ions will be occurring. How interesting. Like a polymer, polyethylene oxide, polycarbonate, polynitrile, polyalcohol, polyamines, all these polymers used in little warmer condition so that they will not only prevent dendrite formation but also allow the ions to flow in the solid state and bring about higher energy density and higher voltage. So this will come maybe in near 20 years or 10 years. The LMBs which were being obsolete by LIBs will be also obsolete by LMBs. How did you like? That's the end of our story. How did you like this program? If you have really liked, why you are greedy to not to hit the like button? Hit the like button, and you have not yet subscribed, please subscribe to my channel SST Chemistry, so that more such interesting videos based on popular science topic, based on your school level topic or higher level topic, as per the requirement. You can also suggest me what you want, on which subject you want under chemistry program, so that I will prepare video for you and that will benefit others. Bye. See you in the next video.